welcome back everyone. So this is actually a back-to-back video. So today, or for this video, I'm going to be analyzing a particle moving through a uniform magnetic field. Now, so currently I think I mentioned this before, but I'm reading Taylor's book on classical mechanics, and I found this topic really interesting. So essentially we want to understand literally how a particle moves through a magnetic field, and this introduces important ideas about complex numbers and how they relate to differential equations. So why don't we begin? So let's start by looking at this specific uniform magnetic field. So let's say we have our three-dimensional coordinates, and we have our uniform magnetic field only going in the z direction. So this is some magnetic field, uniform magnetic field, call it capital B. And then let's say we have some particle here with a velocity v and has charge, I should say, q. Right? Okay. So this is our little particle here, and it's an elementary result that the force on this particle is equal to q times the velocity, taking the cross product with the magnetic field itself. Okay, and by Newton's second law, we can write this as m times the vector a, but the vector a is just going to be the time derivative of velocity. Okay, and to solve this, well, let's just solve it component-wise. So we note that this part is trivial if we consider the components of v to be v1, v2, v3. We can quickly resolve this into its components, and we find that it's just going to be mv1 dot, mv2 dot, and mv3 dot. Okay, and now here we're going to have to value the cross product. And note that, well, since our magnetic field is only going in one direction, this is only going to have a component in the z direction, call it b. Okay? And that's the fact that it's uniform, it's not changing with time. Okay. So when we take the cross product, well, all we're doing here is essentially just, and we'll worry about this little q here at the end of the cross product. So if we take the cross product of v and b, that's going to be the same thing as taking the magnitude of the matrix I hat, j hat, k hat, and then we have, well, v1, v2, v3, and 0, 0, b, which is equal to, okay, we have, let's see, v2 times b, and then we're going to have 0 there. So we take we take I hat times the determinant of this 2 by 2 matrix. So we have v2b I hat minus, let's see, minus v1b j hat, and then we have plus 0 k hat. Okay, so now let's quickly resolve this. So when we multiply q into each of these, well, we're just going to get qv2b as our first component, 2b1b as our second component, and 0 as our third component. So in other words, we have the following. So if we set m1v v1 dot equal to, well, v2 qb, let's just quickly write that out. So we have q v2b is equal to mv1 dot, and then we have q v1, or I should say negative q v1b equals mv2 dot, and finally we have, well, we just have 0 equals mv3 dot. And that actually tells us that the velocity in the z direction is just going to be constant since its derivative is 0. So in other words, that is not going to be very interesting to us, and we're just going to consider the first two of these equations. And in doing so, we're going to project our three-dimensional velocity vector onto the xy plane, and we call that transverse velocity. Okay, so transverse velocity is just going to be just the coordinate, like we project the coordinate onto the xy plane, so like v1, v2. Velocity. Okay, now notice that we can define this coordinate as a complex number. Namely, if we define the Greek letter neta, it's not a very good way of writing it, neta as being, it's kind of like an extended n, neta as being equal to v1 plus v2i. Okay, and that's because, well, note that v1 and v2 are some real numbers. Well, v1 and v2 here are also real numbers, and this, we can cover the entire xy plane with this, with these values. Well, in a sense, this is technically on the imaginary plane, but in a sense, we're still covering all possible values, right? Because we're still covering an entire plane, which is a way of representing our transverse velocity. Okay, now if we take the derivative of this, we have that n dot is equal to, well, let's see, we're going to have, well, v1 dot is, okay, and before I continue, what I'm actually going to do is I'm going to define a parameter which will really simplify these equations. And namely, that parameter is just going to be, it's going to be some lowercase omega equals qb over m. And that implies that qb is equal to m omega. Okay, so if we plug that in, well, what we're going to get is that these equations become, let's see, so if we plug this in here, our m's will cancel and we're going to get w v2 equals v1 dot. And here we're going to get minus w v1 equals v2 dot. This is called a coupled differential equations. Okay, and now if we take the derivative of neta, we're just going to get, well, v1 dot is going to be equal to w v2, and then here we're going to get minus w v1 I. Okay? Now what I want to do is I want to factor out a minus wi. So this equals minus wi times, and then let's see what this is. Well, what this becomes is v2 over minus I. If we multiply the top and bottom by I, this equals I v2 over negative 1 over negative 1, which is equal to I v2. And here we're just going to get v1. So in other words, this just becomes v1 plus v2 I. And this is equal to minus and this becomes minus omega I neta. This is the beautiful thing, because this is a well-known differential equation. It's actually just the exponential function, but I'll quickly rederive it as review. So we can write this instead as d neta dt is equal to minus wi neta, and multiplying both sides by td, it's separable, so when you multiply both sides by dt and divide both sides by neta, we're going to get d neta over neta is equal to minus wi dt. Integrating both sides, we're going to get, well, here we get the natural log of the absolute value of neta equals minus wi t plus c1. Okay, if we take e on both sides, we're just going to get absolute value of neta is equal to some constant c2, which is e to the c1. So c2 e to the minus omega I t, right? And absolute value is just going to be plus or minus. It's just going to be some other constant. We'll call it c. So that gets our final solution for neta, which is neta is equal to c e to the minus omega it. I'm trying not to say w, although that can be pretty easy trap to fall into. So this is essentially our description of how our traverse velocity will move. It won't give the value for our traverse velocity, but at least, well, it'll give the coordinates for our traverse velocity, and it'll give the basic movement, which is exactly what we want. Well, a movement of the velocity vector. And notice that if we kind of quickly can understand what this is telling us, what the movement is showing, is, well, notice that we can write C, we have to write C somewhere on the circle, and we're going to write, let's say, this is C equals some lowercase c, e to the, let's say, I alpha, because this is located somewhere on this, we can represent C as some value on this. It's going to be some initial value, so it has to be located on this circle. And by Euler's great formula, well, this value here, this e to the stuff, is always going to lie in the unit circle. So in other words, c times this is going to lie on the same circle. And again, that's because of basically the Pythagorean identity for trigonometric identities, which is sine squared plus cosine squared equals 1. Because if we take the magnitude of Euler's identity, it's always going to be 1, right? So in other words, we're just going to get that. And notice that this will be rotating clockwise, since it's negative, with the magnitude of Wt by this value here. So we hypothesize that our motion in the magnetic field is going to be some kind of helix, because we're going up at a constant velocity in the z direction. So let's further see why that is. So if we consider another, some other, and I'm going to clear some space here. So if we consider some other complex number z equals, well, xy, so it's going to be like the transverse position, I guess you can say, transverse position, equals xy plus x plus yi. So that models the position. Then it's pretty trivial to see that it's just going to be the integral of our neta. So it's going to be the integral of neta dt, which is, and our neta, well, we saw that our neta, I actually erased it for some reason, but our neta was c times e to the minus w, I should say, minus I minus IWT, right, dt, and using some basic integration, we can find that this is just, well, let's see, so we're going to get, c over minus IW, e to the minus IWT, plus some, now I can't really use C, plus some K. I've never used any other constant of integration except C, so that's kind of strange. I guess I'll just say the word constant. So const. Okay? Okay, so, well, let's see. We can simplify this a bit by multiplying the top and bottom by I. So we're just going to get, let's see, I C over, I'm pretty sure I already said W, over omega e to the I, oh, it's so hard not to say omega, not to say W, plus const. Okay, so let's just write the constant as x plus yi, right? So if we write the constant as x plus yi, well, we're just going to get some value here, right? Now, let's consider the origin to be at xy, and that will take this term to be 0, because then that term will not add any effect. And then that just tells us that, well, we're literally going to have our motion, transverse position to be rotating, on this unit circle, which has radius I c over w. That's unnecessary. The idea is the motion, and we're also going up at a constant velocity, and that tells us we have a helical motion. So I hope you enjoyed that video, and if you want more physics videos, yeah, just tell me, and have a nice day. Goodbye. It's not magnetic.